At the very heart of our Milky Way galaxy, some 26,000 light-years away from Earth, lies one of the most extraordinary objects in the known universe. This object is called Sagittarius A, a supermassive black hole that anchors our entire galaxy in its gravitational embrace. The black hole itself contains roughly 4 million times the mass of our Sun, yet it occupies a region of space smaller than the orbit of Mercury around our star. This incredible density creates a gravitational pull so intense that nothing, not even light itself, can escape once it crosses a boundary known as the event horizon. In May of 2022, astronomers released the first direct image of Sagittarius A, a feat that required coordinating 8 radio telescopes across the entire planet to create what scientists call an Earth-sized telescope. The image showed a glowing ring of superheated material swirling around a dark central region, the shadow of the black hole itself. This photograph represented the culmination of decades of work and confirmed what scientists had long suspected about the nature of our galactic center. The glowing ring appears orange and yellow in the processed images, though in reality these are false colors representing radio wave emissions that our eyes could never naturally perceive. The environment immediately surrounding Sagittarius A is unlike anything found elsewhere in our galaxy. Here, space and time themselves become warped and twisted by the immense gravitational forces at play. Stars orbit the black hole at speeds that can reach several percent of the speed of light, completing orbits that would take our Sun millions of years to traverse in mere decades or even years. One particular star, designated S2, completes a full orbit around Sagittarius A in just 16 years, reaching speeds of nearly 5,000 kilometers per second at its closest approach. These stellar velocities are so extreme that astronomers can actually observe the effects of Einstein's theory of general relativity in action, watching as the orbits themselves shift and precess in ways that Newton's classical physics could never predict. The region within a few light years of the galactic center contains more stars packed into a small volume than anywhere else in the Milky Way. Scientists estimate that within just 3 light years of Sagittarius A, there may be as many as 10 million stars compared to the relative isolation of our own Sun, which has no stellar neighbors within 4 light years. This dense stellar environment creates a complex gravitational dance, with stars constantly influencing one another's paths, occasionally colliding, and sometimes being flung out into the broader galaxy at tremendous speeds. Surrounding the supermassive black hole is a structure called an accretion disk, a swirling maelstrom of gas, dust, and stellar debris that spirals inward toward the event horizon. As this material falls toward the black hole, it accelerates to tremendous velocities and heats up through friction and compression, reaching temperatures of millions of degrees. At these temperatures, the material emits radiation across the electromagnetic spectrum, from radio waves to X-rays. However, Sagittarius A is actually quite dim for a supermassive black hole of its size, suggesting that it is not currently consuming large amounts of material. The black hole appears to be in a relatively quiet phase, feeding only sporadically on stray gas clouds or debris from passing stars. The discovery of what lies at the center of our galaxy required overcoming tremendous observational challenges. The galactic center sits hidden behind vast clouds of dust and gas that block visible light, making it impossible to see with ordinary optical telescopes. Instead, astronomers had to use radio waves and infrared light, which can penetrate these obscuring clouds. In the 1970s, scientists using radio telescopes detected a bright, compact source of radio emission coming from the direction of the galactic center. This source, which they named Sagittarius A, after the constellation Sagittarius, where it appears in our sky, remained mysterious for years. The real breakthrough came in the 1990s when astronomers using infrared telescopes began tracking the motions of individual stars near the galactic center. By following these stars over many years, scientists could map their orbits with increasing precision. They found that the stars were orbiting around a common point, moving in elliptical paths that clearly indicated the presence of an enormous concentrated mass. Yet, when they looked at that central point, they found nothing visible. The only explanation that made sense was that the stars were orbiting a supermassive black hole. One of the most remarkable aspects of Sagittarius A is how it affects the very fabric of spacetime around it. According to Einstein's general theory of relativity, massive objects curve the space and time in their vicinity, and nowhere is this curvature more extreme than near a black hole. As you approach Sagittarius A, space becomes increasingly warped. A journey that would take a certain distance in flat space becomes stretched and elongated. Time itself runs differently at different distances from the black hole. A clock placed near the event horizon would tick more slowly compared to a clock farther away, an effect called gravitational time dilation. The event horizon of Sagittarius A, the point of no return from which nothing can escape, has a radius of about 12 million kilometers. This might sound large, but it is actually quite small compared to the black hole's mass. For comparison, the orbit of Mercury around our Sun has a radius of about 58 million kilometers, nearly 5 times larger than the event horizon of our galaxy's central black hole. Yet this relatively small region contains the mass of 4 million suns, creating a density that defies ordinary comprehension. Beyond the event horizon lies the singularity, a point where the curvature of spacetime becomes infinite and the known laws of physics break down. What actually happens at the singularity remains one of the great unsolved mysteries of physics. The mathematics of general relativity predict that all the mass of the black hole becomes compressed into an infinitely small point. But many physicists suspect that this prediction signals the need for a deeper theory that unites general relativity with quantum mechanics. Understanding what truly lies at the center of a black hole may require a complete revolution in our understanding of reality itself. The galactic center region also hosts some of the most energetic phenomena in our galaxy. Jets of particles and radiation occasionally burst outward from near the black hole, powered by the magnetic fields that thread through the accretion disk. These jets can extend for light years into space, carrying energy and material away from the black hole at velocities approaching the speed of light. The exact mechanism that creates these jets is still not completely understood, but they appear to be related to the rotation of the black hole itself and the magnetic fields in the surrounding plasma. Scientists have also discovered massive lobes of gamma-ray emission extending above and below the galactic center, structures called the Fermi bubbles. These enormous structures span some 50,000 light-years from top to bottom, dwarfing even our Sun's distance from the galactic center. The bubbles appear to have been created by a massive burst of activity from Sagittarius A that occurred millions of years ago, when the black hole consumed a large amount of material in a relatively short period. This finding suggests that our galactic center has not always been as quiet as it is today, and that Sagittarius A may undergo periodic episodes of intense feeding and activity. The stars that orbit closest to Sagittarius A experience conditions unlike those anywhere else in our galaxy. Some of these stars are massive, young, and hot, which puzzles astronomers because the intense tidal forces near the black hole should make it nearly impossible for stars to form there. The current leading theory suggests that these stars actually formed farther away and later migrated inward, perhaps forming in a disk of material that once surrounded the black hole, or perhaps being captured from passing star clusters. Some of these stars will eventually venture too close to the black hole and be torn apart by tidal forces in what astronomers call a tidal disruption event, their material stretched into long streams that spiral into the black hole. The magnetic fields around Sagittarius A play a crucial role in shaping the flow of material and energy in the galactic center. These fields are generated by the motion of charged particles in the accretion disk and can become twisted and amplified to tremendous strengths. The magnetic pressure can sometimes become strong enough to partially support material against the inward pull of gravity, influencing how and when material falls into the black hole. Understanding these magnetic fields and their behavior requires sophisticated computer simulations that model the complex interplay between gravity, magnetism, and the flow of hot plasma. Black holes like Sagittarius A may have played a fundamental role in the formation and evolution of galaxies throughout the universe. Astronomers have found that nearly every large galaxy appears to have a supermassive black hole at its center, and there seems to be a relationship between the mass of the black hole and the properties of the galaxy that hosts it. This suggests that black holes and their galaxies grow together over cosmic time, each influencing the other's development. The energy released by actively feeding black holes can heat up gas throughout the galaxy, regulating star formation and shaping the galaxy's structure. Our own Milky Way appears to have grown through mergers with smaller galaxies over billions of years, and each merger may have brought its own central black hole, which then merged with Sagittarius A. The technique used to image Sagittarius A, called Very Long Baseline Interferometry, represents one of the most impressive technological achievements in astronomy. By combining observations from radio telescopes separated by thousands of kilometers, astronomers can achieve angular resolution equivalent to a telescope the size of the Earth. The data from each telescope is precisely time-stamped using atomic clocks, then correlated together using powerful supercomputers. Creating the image of Sagittarius A required processing petabytes of data and developing new algorithms to account for the complex structure and rapid variability of the emission. The glowing material around the black hole changes on timescales of minutes, much faster than the days required to collect the complete dataset, which meant that scientists had to develop special techniques to extract a coherent image from the observations. The discovery and imaging of Sagittarius A has answered many questions about our galaxy, but has also raised new ones. Scientists are particularly interested in understanding how supermassive black holes form in the first place. The black holes we observe today contain millions or even billions of solar masses, but they must have started from something. Some theories suggest they grew from the remnants of the first generation of stars in the early universe. Others propose that they formed from the direct collapse of massive gas clouds. Understanding the origin of supermassive black holes requires looking back to the very early universe, when galaxies were just beginning to form. The rotation of Sagittarius A is another topic of intense study. Like all black holes, Sagittarius A likely rotates, and this rotation has important consequences for the surrounding environment. A rotating black hole drags spacetime itself around with it, an effect called frame dragging. The rotation also affects the structure of the event horizon and the behavior of matter in the accretion disk. By studying the emission from near the black hole and the orbits of nearby stars, scientists hope to measure how fast Sagittarius A is spinning. Current estimates suggest it may be rotating at a significant fraction of the maximum possible rate, though the exact value remains uncertain. The broader galactic center region extends for hundreds of light years around Sagittarius A and contains a rich variety of astronomical objects. Dense molecular clouds fill much of this region, providing the raw material for ongoing star formation despite the harsh environment. These clouds sometimes collide with the streams of material flowing toward or away from the black hole, creating shock waves that light up in infrared and radio emission. X-ray observations have revealed diffuse hot gas filling the region, heated to millions of degrees by stellar winds, supernova explosions, and outflows from the black hole. Radio observations of the galactic center have revealed mysterious filamentary structures, long, thin strands of material that appear to be aligned with the large-scale magnetic field of the galaxy. These structures, some of which stretch for over 100 light-years, remain poorly understood, but may be related to the energy and particles flowing outward from the central regions. The magnetic fields in these filaments must be quite strong to make them visible against the background emission, suggesting they may be sites where cosmic rays are accelerated to high energies. Historical observations of the galactic center show that it has not always been as quiet as it appears today. Ancient gas clouds still bear the imprint of a powerful outburst that occurred just a few hundred years ago in human timescales. This event, sometimes called the Seyfert flare, after the astronomer who first hypothesized similar phenomena in other galaxies, briefly increased the brightness of Sagittarius A by perhaps a factor of 1,000,000. The radiation from this event is still propagating outward through the galaxy, lighting up distant clouds like an echo of the past. Such outbursts may occur whenever the black hole captures a particularly large amount of material, perhaps from a passing gas cloud or a disrupted star. The study of Sagittarius A and the galactic center has required developing new technologies and techniques across multiple wavelengths of light. Infrared astronomy has been particularly important, as infrared light can penetrate the dust that blocks visible light while still providing sharp enough images to track individual stars. The development of adaptive optic systems, which use deformable mirrors to correct for the blurring effects of Earth's atmosphere, has been crucial for achieving the resolution needed to study the region in detail. Similarly, advances in detector technology have allowed astronomers to record increasingly faint sources and capture rapid variability. Our understanding of black holes has evolved tremendously over the past century. When Einstein first published his general theory of relativity in 1915, the solutions to his equations that described black holes seemed like mathematical curiosities rather than real objects. The term black hole itself was not coined until 1967 by physicist John Wheeler. The idea that such objects could actually exist in nature, let alone that one might sit at the center of our own galaxy, would have seemed like science fiction to most scientists of that era. Yet observation after observation confirmed the theoretical predictions, and black holes have become recognized as some of the most important objects in the universe. The gravitational influence of Sagittarius A extends far beyond its immediate vicinity. The black hole's gravity helps to shape the orbits of stars throughout the inner region of our galaxy, and its presence affects the overall distribution of matter in the galactic center. Computer simulations of galactic evolution show that the supermassive black hole acts as a kind of anchor point, helping to stabilize the central regions of the galaxy against disruption from passing galaxies or large-scale flows of dark matter. Future observations of Sagittarius A promise to reveal even more about this remarkable object. The Event Horizon Telescope continues to take data with improved sensitivity and additional telescopes joining the network. Scientists hope to create videos showing how the emission around the black hole changes with time, which would provide new insights into the physics of accretion and the behavior of matter in extreme gravitational fields. New infrared instruments on large ground-based telescopes and space missions will allow even more precise tracking of stars near the black hole, potentially revealing effects like the frame dragging caused by the black hole's rotation. The question of what lies at the center of the Milky Way has a simple answer in one sense. At the very center sits Sagittarius A star, a supermassive black hole containing 4 million solar masses. Yet this simple answer opens up vast depths of complexity and mystery. The physics of black holes connects to the deepest questions in science, from the nature of space and time to the origin and fate of the universe itself. The galactic center serves as a natural laboratory where we can test our theories under the most extreme conditions imaginable, where gravity becomes so strong that it dominates over all other forces, and where the predictions of general relativity can be tested with exquisite precision. The continuing study of what lies at the center of our galaxy reminds us of how much we have learned about the cosmos and how much remains to be discovered. Each new observation brings fresh surprises and challenges our understanding. The universe continues to reveal itself as stranger and more wonderful than we ever imagined, with mysteries that inspire each new generation of scientists to push the boundaries of knowledge ever further into the unknown.